आज हम एक नया कॉन्सेप्ट देखेंगे. Let's consider fair coin toss. Okay. And let's call this experiment number 1. Experiment number 1. You have a fair coin, you toss it. What will be your sample space? Let's call it S1, the sample space for experiment 1. You have a fair coin, you toss it. What will the sample space contain? Head and tail. Okay, great. Let's consider experiment 2 as well. And in experiment 2, you have you roll a fair die. In this experiment, the sample space for experiment number 2, S2, will be a set. It will contain which elements?
1, 2, 3, 4, 5.
1, 2, 3, 4, 5, 6. Great. In sample space 1 for experiment 1, let's say you have an event A, and that event is this. What does this event mean? Yani, you tossed a coin and you got a head. ठीक है, ये आपका event A है. What's the probability of event A?
1/2.
1/2 because it's a fair coin, so it's a simple sample space. Size of A is 1. A has only one element, and the sample space has 2 elements. So the probability is half. Now for experiment 2, consider an event B, and that is this event. What does this mean? कौन सा event है? You rolled a die and you got a 4. Okay, so what's the probability of B?
1/6.
Why?
1/6.
Why?
Size of B or size of S?
Size of B is 1 element and S2 contains 6 elements. Can we count? Should we use counting in this space, sample space?
Yes, sir.
Why? Why?
Countable.
You should use just one word. Your sample space is simple. When you say it's simple, it means it's finite. It means it's equilikely. So in equilikely finite spaces, that is in simple sample spaces, you can use counting. Okay, great. Now consider the following event. Consider the event head on coin toss and 4 on die roll. So what's this event? कि आपने कॉइन टॉस किया और कॉइन टॉस करने के बाद हेड आ गया और आपने डाई रोल किया, डाई पे 4 आ गया, 4. ओके. माय क्वेश्चन इज which sample space does this event belong to? किस सैंपल स्पेस का इवेंट? S1 का है ये?
सर दोनों का है।
इसका मतलब S1 का भी है. If you say both, then it means it belongs to S1. Can you have a 4 in sample space 1?
No sir, नहीं.
So S1 का नहीं. S2, does it belong to S2?
Yes, sir.
Yes sir.
So you can have a head on in sample space S2.
नहीं.
No, sir.
So this event, head on coin toss and 4 on die roll, this neither belongs to sample space 1 nor does it belong to sample space 2. This event belongs to neither of them, which means this event is neither an outcome of the first experiment nor an outcome of the second experiment. ये दोनों एक्सपेरिमेंट से उनकी जो आउटकम्स हैं, मतलब सिर्फ एक्सपेरिमेंट 1 से ये थर्ड इवेंट नहीं आ सकता. सिमिलरली सिर्फ एक्सपेरिमेंट 2 से ये इवेंट नहीं बन सकता. ओके. This event that I've written, head on coin toss and 4 on die roll, it's the outcome of a third experiment. ये किसी और एक्सपेरिमेंट की आउटकम है.
इसलिए दोबारा सैंपल पे लगाई पड़ेगी, लाइक इसमें हेड की और इसमें डाइस के सारे में.
Yes, okay, let's make it with so this experiment, this third experiment will have a sample space, let's call it S3, sample space for the third experiment. And what will this contain?
सर यहाँ पे A यूनियन, सर यहाँ पे हम A यूनियन B का इवेंट कह सकते हैं कि A यूनियन B कर लो.
You may or you may not, but right now what I want to know is, can such an event, head on coin toss and 4 on die roll, can such an event occur after experiment 1 only? And can such an event
एक एक्सपेरिमेंट से तो कभी नहीं आएगा. A यूनियन B या जब दोनों का होगा बोथ होंगे तो फिर हमारे पास
so
ये अकर होगा.
so you're saying that we'll have to do both experiments? Is that
Yes, sir.
That means that you did that. That's a third experiment then. Your whole description of the experiment will be take a fair coin, toss it, then take a fair die, roll it. That's a third experiment. It's made up of these two experiments, but it's a separate experiment. All right?
Okay, sir.
Okay. Now, what will be the sample space of this third experiment? What are the possible outcomes of this third experiment? Anyone? Can you guys help me out?
Sir, head 1, head 2, head 3, head 4, head 5, head 6 with tail 1, tail 2, tail 3.
Absolutely.
Tail
Head 1, head and 2, head and 3, head and 4, head and 5, head and 6, and similarly tail and 1, tail and 2, tail 3, tail 4, tail on coin and 5 on the die, and finally tail on the coin and 6 on the die. All right. Now, which element of the sample space makes up my event? Head on coin toss and 4 on die roll. Which one?
सर एक ही है, हेड कॉमा 4.
Head comma 4. Great. So we can write probability of this event, head on coin toss and 4 on die roll. Now you can write this probability in many different ways, and over the course we'll use different ways to write these probabilities. So let me write them. Sometimes you will write it like this, like you will describe it in English, or you could say probability of some set, and that set contains the following element of the sample space, right? This is how we wrote each element of the sample space. Now I have a set that contains only one element, and that element is h comma 4. You can write it like this. You can also write it like this. Probability, sometimes you, this is an abuse of notation, but sometimes you just write it like this. That's an abuse of notation. Technically, you should have these curly braces because you want to have a set over here. But sometimes we abuse notation and we write it in short form. But you should understand what this means. And another way of saying this is probability of head intersection 4. This might also be an abuse of notation, but this intersection just replaces the and. Probability of head on coin toss and 4 on the die roll. And what's the answer? What's the answer for this probability? Anyone? 1 over 12. Why?
1 over 12.
Why?
Size of sample is 12 and the event is occurring only once.
How do you know that the size of the sample space is 12?
By counting.
Why did you count?
Finite equivalently. Simple
These are bad answers. They are countable, that's why I counted. Bad answer. They are finite, that's why I counted. Bad answer. They are bounded, that's why I counted. Bad answer. There is only one good answer. It's a simple sample space. Why is it a simple sample space? How do you know?
It's finite and it's equivalent.
Why is it equilikely? How do you know?
Sir, because the coin is fair. Yes, sir.
Okay, because the coin is fair, so you could land on the first row or on the second row. Okay, and and the die is also fair, so you could land at 1, 2, 3, 4, 5, 6. So all 12 of these, or each of these 12 options has the same chance. And so, okay, good. Now you can count the size of the sample space. S3 is 12, and the size of your event is 1. And so you get 1 over 12. Okay. Now I want you guys to notice something, which we will come back to later. That the probability of head and 4, which came out to be 1 over 12, and the probability of event A. What was event A in experiment 1? Head, right? That probability was 1 over 2. And what was the probability of getting a 4? Anyone?
1
over 6. What happens when you multiply them? Okay. Yeah, this was half. This was 1 over 6. And oops. So this probability of intersection can be, it seems that the probability of intersection is equal to the product of these individual probabilities, right? Now we have to see whether this happens every time or not. Okay. And this probability of intersection, we call it the joint probability. Right? It's called the joint probability. The probability of one event happening and another event happening. The probability of intersection, whenever you have the intersection, the probability of intersection is called the joint probability. And while we're at it, these individual probabilities, the probability of one of those events is called a marginal probability. Similarly, the probability of the other event, because it's just one event, this is also called a marginal probability. Okay, so that's just some new terminology. Okay. Now let me ask you a question. Is it clear so far? Are there any questions? Now let me ask you a question. Question number 1. We've conducted 3 experiments. Which of these 3 experiments will require the most effort? Anyone? Will experiment 1 take the most effort?
Third.
Experiment 3 will be the
Experiment
hardest.
3.
Why?
The third one.
Okay, so it's The third one,
उसकी sample space बड़ी
करना पड़ेगा फिर दिया जाएगा.
yes, because we have to toss the coin and then we have to roll the die. So we have to do both things. So it's the hardest. Okay, and the sample space will be the largest. Okay, fine, good. Let me ask you question 2. Does experiment 1 influence the result of experiment 2 in any way? Does the coin toss influence the die roll?
No, sir.
They're both independent.
Okay, so you're saying no, it doesn't. Okay. Does experiment 2, the die roll, does that influence experiment 1? In any way?
No, sir.
No, sir.
Okay, no. Don't influence. Okay, great. Let's define this influence. When I say influence, and when you say it doesn't influence, what you're saying is that it does not increase, decrease, or block the chances of anything that is going to happen in the other experiment, right? If you get a head on the coin toss, it does not increase the chance of getting a 4 on the die roll. It does not decrease the chance of getting a 4 on the die roll. It does not block getting a 4 on the die roll. All right, so that's what I mean by influence. Okay. Okay, great. So such experiments that do not influence each other in any way, such experiments that do not influence each other are called independent. Independent. So that's a new term that we've mentioned today. Okay. Output of the coin toss is independent. That's how you say it. Output of the coin toss is independent of the output of the die roll, and vice versa. The output of the die roll is independent of the output of the coin toss. And we saw over here there seems to be a rule for independent events. There seems to be a rule for independent events because the coin and the die roll, the coin toss and the die roll were independent. Their individual probabilities, probability of head was half, probability of 4 on the die roll was 1 over 6. When we multiplied them, we got 1 over 12. And we also saw that the joint probability of head, probability of head and 4, that came out to be 1 over 12 as well, which was the product of the marginal probabilities. Okay, so it seems to be a rule. So let's write this rule. Let's write this rule. for independent events A and B, their joint probability probability of A intersection B, sometimes written as probability of A comma B, and well, there is even more notation. Sometimes this is also written like this, probability of AB, sometimes. Okay, so you should be aware of these notations. The joint probability can be computed via the smaller sample spaces. S1 and S2. Remember, this event was from sample space S3. Okay, and we can compute the probability of this event from a larger sample space using events from these smaller sample spaces S1 and S2, using the formula probability of A intersection B equals probability of A multiplied by probability of B. Okay, where this is the joint probability, this one is the marginal probability, this one is also a marginal probability. Okay, and independent events like the coin toss and the die roll, independent events are also called, I'm just going to give you just two technical names, technical terms. You can just continue calling them independent events, but sometimes in some books or some research papers or some blogs, you'll read that independent events are called either probabilistically independent, or sometimes it's written stochastically independent. Okay, so whenever you see this fancy word stochastic, just replace it with probabilistic. Okay, stochastically just makes you sound like you know something. Okay, one more point. Sometimes independence can be seen intuitively. Sometimes independence can be seen intuitively. For example, it was intuitively obvious, यानी आप अपने जहन से वैसे ही सोच के बता सकते थे. It was intuitively obvious कि the coin toss and the die roll will not influence each other. It was obvious to you. You don't need to do an experiment. It's just obvious to you that a coin toss will not influence a die roll. So this kind of independence is intuitively obvious. Such as such as this coin and die example. But sometimes events can be independent, but it's not intuitively obvious. And in today's lecture, we'll look at an example, right? Which means that this concept of independence in independent events, you have some events that are intuitively independent. It's easy to see that they will be independent. It's easy to see that there can be no connection between these events. And then there can be some events where it's not easy to see whether there will be a connection between them or not. But they will follow this rule that their joint probability comes out to be equal to the product of their marginals. This is the definition of independence. This right here is the definition of independence, whether the events are intuitively independent or not. आपको समझ लगे या ना लगे कि ये इंडिपेंडेंट होंगे या नहीं होंगे, अगर वो ये रूल फॉलो करते हैं, अगर उनकी जॉइंट प्रोबेबिलिटी इक्वल्स the product of their individual probabilities, marginal probabilities, then you will call those events independent, right? So this stochastic or probabilistic independence, that's a more general term because that's what is implied by the formula. And then within all these independent events, you'll have some events that might be intuitively obvious, intuitively independent. Okay, let's do some examples. Are there any questions so far?
No, sir.
Okay, let's do a question. Let's do two questions, which will hopefully make it more clear what we mean by intuitively obvious. Okay, first question. Let a point be selected at random from a square, and the range of this square is 0 to 4 by 0 till 4. Can anyone describe what is happening here? 0, 4 and then 0, 4. What is happening here? What does this mean? Anyone?
Area of square.
Nope. In a sense, yes. I am describing the extent of the square. Where does the square begin and where does it end? This is the range of the square on the x-axis, x range. That the square starts at x equals 0 and ends at x equals 4, both included. So it's 0 till 4 by 0 till 4 on the y-axis. So that's the y range. Right? Can we draw this? We'll draw this later. Okay. Let A be the event. Let A be the event that selected point lies inside the rectangle. And what's the rectangle? The rectangle is 13 by 04. Okay. And let B be the event that the selected point lies in another rectangle. So these are two events, and the question is this: are events A and B independent? Now, before you try to answer this question, I want to ask you, can you intuitively tell whether A will influence B or B will influence A? Is it intuitively obvious that A and B are independent or not independent? For example, it was intuitively obvious to you that the coin toss will not influence the die roll. Is it that obvious over here?
No, sir.
No, it's not straightforward. I mean, it's not easy to see if they're independent or if they're not independent. Can't tell. So let's try to solve this. How do you solve probability questions? First, you look at the sample space. Your point is selected at random from a square, so that's your sample space. Can you draw your sample space? Let's draw the sample space. That's your x-axis. That's your y-axis. The extent of the square starts from x equals 0 and goes till x equals 4. And on the y-axis, the square starts from y equals 0 and goes till y equals 4, which means that this is my square, right? That's my sample space. Can anyone make event A for me? Can we visualize event A? Anyone? What do I do? Event A is a rectangle. That's what the question says. Which rectangle is it? Event A. Anyone?
The X range will be starting from 1 and ending at 3.
So we start at 1 and we end at 3. And what about the Y range?
Y range 0 to 4. Very same.
So the rectangle might be something like this, right? That's event A. What about event B? Quickly.
Y-axis 1 और 3 के दरमियान होगा
Or X?
That's 4, the 0 is 4.
Yeah, so that's 3 and that's 1, and so that's my event B. That's the area that it covers. What is this region? This region over in the middle.
A intersection B.
That's A intersection B. A intersection B. Okay. Now, when will you accept that A and B are independent? When should one say that A and B are independent?
When the joint probability is equal to the product of marginal probability.
Absolutely. Absolutely. For independence, probability of A, B or A intersection B should be equal to probability of A into probability of B. Let's see if that is true. Let's see if that holds. If it's true, then they're independent. If it's not true, then they're not independent. So, what is probability of A? Quickly. You guys should be experts at this by now. What's the rule that you use? What's the first rule? Size. And since these are measurable sets, they're not countable sets, they're measurable. How will you compute this size?
Area.
Good. Area of A over area of S. Keep going. Keep going. What do we do now? What's area of A?
8.
The area of A is, so the width is 2 and the height is 4. So that's, let's do it properly. 3 minus 1 multiplied by 4 minus 0. That's the area of A. And the area of the sample space is 4 minus 0 multiplied by 4 minus 0. So that's 8 by 16, which is half. Okay. What is the probability of B? Are there any questions on probability of A? Or is it clear? Similarly, probability of B will also be half. You can do the math. You can do the math. The probability of B will also be half. And you can see it's the exact same area. It's just the rectangle is rotated 90 degrees. And what's the probability of this purple region, A intersection B? That's equal to area of A intersection B divided by area of the sample space. And what is the area of A intersection B? Anyone?
So 4. 3 minus 1 into 3 minus 1.
Absolutely. So the x range is from 1 till 3. The y range is also from 1 till 3. So the width and the height is 2. The area of the sample space is 16. So that's 2 into 2, 4 by 16, which is equal to 1 by 4. Now you guys tell me, are they independent?
Yes, sir, independent.
Yes, sir. Yes, sir. Independent.
Since probability of intersection B equals 1 over 4, which is equal to half into half, which is equal to probability of A into probability of B, A and B are independent events. So they are stochastically independent. That's what you say. They might not be intuitively independent. It might not be intuitively obvious that they're independent, but stochastically, which means as long as they follow this formula, as long as they follow this condition, they are stochastically independent. Should we do another question? Let's do another question. Okay. Now I want you to consider randomly selecting a family of 3 children. And that's your experiment. You randomly select a family that has 3 children. What will your sample space look like? Anyone?
Five pupil.
5. Okay, that's a good answer. But I'm only concerned with the children, not the parents.
3 pupil.
Okay, good. 3 pupil. And give me one possible outcome.
2 boys and a girl.
The three.
Okay, great. So let's start enumerating. So you could have all 3 boys. You could have boy, boy, girl. You could have boy, girl, boy. You could have girl, boy, and boy. You could have girl, girl and boy. You could have girl, boy, and girl. You could have what else? Boy, girl, girl, and you could have girl, girl, girl. Are there any other possibilities?
सर ये जो सेकंड और थर्ड है ये तो सेम ही होगा दो लड़के एक लड़की
Yeah, if you were counting the number of boys, then outcomes number 2, 3 and 4, they're the same, right? Outcome number 2, 3 and 4, they're the same if you were counting the boys. But we're not counting the boys, we're just looking at a family. And so the first child is a boy, the second child is a boy, the third child is a boy. Okay, that's one outcome. Another outcome is first 2 children are boys, third is girl. Third outcome, the first child is a boy, the second child is a girl, third child is a boy. Alright, that's why we're saying that these are all the possible outcomes. If you were counting, then some outcomes will become the same. But I'm not counting. Are there any more outcomes? Or is it the whole sample space? How will I know? What should be the size of the sample space without enumerating the sample space?
Sir, 2
2
power n.
raised to power 3, 8 sample space.
Which rule? That's a correct answer. Which rule have you used? Which principle have you used? Multiplication principle. You had 3 spaces to fill. Each space could have been filled in 2 ways. You could have boy or a girl. 2 multiplied by 2 multiplied by 2. So that's 2 to the power 3. That's 8. And you have all 8 outcomes in this set. So that's your sample space. Okay, great. Let's assume for this question, let's assume that S is a simple sample space. All 8 outcomes are equally likely. We don't know whether they are in reality or not, but let's assume they're simple. Let A be the event. The family has both boys and girls. That's the event. Let B be the event. Family has at most 1 girl. I ask you the same question again. Are A and B independent events? And before we answer this, first answer the other question. Is it intuitively obvious? Is it intuitively obvious to you that A and B will be independent events?
No, sir.
I mean, it's not straightforward. It's not easy to say that if a family has both boys and girls, then this will not influence the other event that the family has at most one girl. It's not intuitively obvious. Okay. So let's do it the stochastic way. Let's do it the proper way. How should I proceed? What should I do? Let's enumerate these sets. What will they contain? So in the question, I have described these sets. I've just described them. I haven't given you the sets. I've described them. But now I want you to give me the sets. What elements are in this set? A. Family has both boys and girls. Which elements, which outcomes should be in this event? Anyone?
So first और 8 के अलावा मैं आने सारे हैं.
Okay, only the first one and the last one. The first one is all boys and the last one is all girls. So all the rest should be in event A. Let me just copy them. Okay, great. And since it's a simple sample space, I can compute the size by counting, and the size of A is 6. The size of the sample space is 8. What is set B? Family has at most one girl. Oh wait, I moved it. Oh, wait. Okay. What will you have in, which elements will you get in set B? Family has at most one girl.
सर सेट ए वाले तो सारे ही आ जाएंगे और जो है ना सिर्फ ट्रिपल गर्ल्स वाला वो एक ऐड होगा.
Sir, first 4 elements of the sample space.
सर ये तो एट मोस्ट है ना, जिसमें मतलब सिर्फ एक ही गर्ल
भी हो सकते हैं.
Absolutely, this is the correct answer. Only the first 4. In the first one you have no girls. In the second one you have one girl. Third one, one girl. Fourth one, one girl. In all the remaining you have either 2 girls or 3. That's more than 1. So only these first 4 will come. Okay. That's my set B. Great. And because it's a simple sample space, set size can be computed by counting. And that's 4. Okay, now solve the question. Anyone? Probability of A, 6/8. Probability of B.
सर एक सेट बी को अगर हम बता दें डाटा लिखना.
Okay. Just look at the set B that I've made. If it makes sense, if it doesn't make sense, let me know. I'll continue. If it doesn't make sense, just interrupt me again. All right? Just try to.
मोस्ट वाली समझ नहीं आ रही.
Delete हो रही.
सर पता नहीं, मुझे तो समझ नहीं आया ये.
इसको सोचिएगा.
सर ज्यादा से ज्यादा 1 घंटा हो सकती है और कम से कम कोई भी नहीं हो सकती.
बस फिर तो कम से कम इसमें है ना 0. So this is 4/8. Now let's consider this other event. A and B, A intersection B. What will you have in this set? A intersection B. Which elements? You have both sets in front of you. You can find the common elements here.
So 6 over 8 multiplied by 4 over 8.
No, I'm not asking you about any probabilities.
First 3 elements.
So 3 elements होंगे.
These three.
Yes, sir.
You don't. Okay, you don't have the first one in A. Okay. B, boy, boy, girl, you have it here in A. Boy, girl, boy, you have it here in A. Girl, boy, boy, you have it here in A. So these three are common. Okay. So these are my three. And this means that the size of A intersection B is 3, and which means that the probability of A intersection B should be equal to 3 over 8. So we have all three probabilities. Now we just have to see if 3 over 8 is equal to 6 over 8 into 4 over 8. Is it?
Yes, sir.
So let's do P of A into P of B, which is equal to 6 over 8 into 4 over 8. So this is 1 over 2. That's 3. So that's equal to 3 over 8, which is equal to probability of A intersection B as well. Therefore, they are independent. And it wasn't intuitively obvious, so they're stochastically independent. Okay, let's continue. Now I have, so what if I have 3 events? Till now, we have discussed event A and event B and discussed independence of 2 events, A and B. What if you have 3 events? Okay. And 3 events are A, B, and C. For such events, if, okay, now you have 3 events, A, B, and C. If probability of A and B equals probability of A multiplied by probability of B, तो आप क्या कहेंगे? A और B को क्या कहेंगे? What will you call A and B?
Independent.
So A and B are independent because joint equals product of marginals. And if, in addition, if A and C, if probability of AC equals probability of A multiplied by probability of C, then A and C are also independent. And if in addition probability of B and C equals probability of B multiplied by probability of C, then you'll say that B and C are also independent. And these are all the pairs that you could make. With 3 events A, B, C, you can make 3 pairs A, B, A, C, and B, C. If all of these things hold, then you will say that A, B, and C events are pairwise independent. Like every pair among them is independent, right? Sometimes I will just write PI, pairwise independent. But if in addition to being pairwise independent, if these 3 things hold, and in addition probability of A, B, and C can be written as, if it can be written as, right? If this is true, then you will say that A, B, and C are mutually independent. And sometimes I'll write it like MI. Okay, so in order for them to be mutually independent, all of the pairs will be pairwise independent, and all three events themselves, their joint probability of A, B, C, will be equal to the product of their marginals, individual probabilities. Okay, then you will call them mutually independent. Okay. Now in the time that remains, I want you to really focus, and I want you to be quick in your answers. मैं चाहूँगा कि आप अपना ज़हन मेरे ज़हन के साथ मिलाएं, ठीक है? मेरे साथ चलना है। अब मैं थोड़ा तेज़ चलूँगा, मेरे साथ चलना है आपने, ठीक है? We have studied the case 3 heads in 4 tosses of fair coin. ये हम कर चुके हैं। 3 heads in 4 tosses of fair coin, ये किसी पहले लेक्चर्स में हमने देखा था ये। But what about 3 heads in 4 tosses of a biased coin? How will you find these probabilities?
Sir, biased sample space is simple.
Exactly, over there the sample space was simple, which meant that you could compute probabilities via, or sizes by counting, and therefore probabilities by counting. Now the sample space is not going to be simple, and so how do you compute probabilities in such a sample space? So let's see. Before we study this, let's see what we have already studied and what we need to study more. We have covered independence. Now you know what independent events are. They don't influence each other, and their joint probability equals the product of their individual probabilities. Let's cover something more. There's something called mutually exclusive events. Have you heard this term before? Anyone? Mutually exclusive events. It means if A has occurred, then B definitely did not and cannot occur. A excludes B. And let me give you an example. Head and tail on coin toss are mutually exclusive. ME, mutually exclusive. Is it true? Are head and tail on a coin toss, they are mutually exclusive. Why?
बिकॉज सर अगर हेड आया तो फिर टेल नहीं आ सकता ना, अगर टेल आया तो फिर हेड तो डेफिनेटली नहीं आ सकेगा.
Absolutely. And this is the whole definition of mutually exclusive. कि अगर एक इवेंट हो गया है तो फिर बाकी नहीं हो सकते. ठीक है, that's mutually exclusive. Let's do another example. Die roll 1, 2, 3, 4, 5, 6 on die roll. Are they mutually exclusive?
Yes, sir.
They are mutually exclusive. If I tell you that I got a 4, it means I didn't get a 1, I didn't get a 2, I didn't get a 3, I didn't get a 5, and I didn't get a 6. If I tell you I got a 6, it means I did not get all the other 5 numbers. If I tell you I got a 2, it means I didn't get the other 5 numbers. So they're mutually exclusive. That's what it means. And in terms of sets, mutually exclusive events will be drawn like this. If this is event A, and if A is mutually exclusive to B, if A and B are mutually exclusive, then they will not have any intersection. Because if you're in set A, it means that you're not in set B. It means set B cannot occur. If you're in set B, it means you're not in set A, which means set A cannot occur. So that's mutually exclusive. So, is it true that if A and B are mutually exclusive, then A intersection B is the null set? Is this true? Is an empty set? Yes, it's an empty set.
Yes,
Yes.
sir.
And we write the empty set like this, like a null set. It contains nothing. Okay. And we have also seen a rule which says probability of A union B equals probability of A plus probability of B minus probability of A intersection B. Do you remember this rule? We studied this earlier.
Yes, sir.
Yes, sir.
So what will this rule look like for mutually exclusive events?
A intersection भी 0 हो जाएगा तो हम उसको neglect कर देंगे.
Exactly. For mutually exclusive events, probability of A union B will be equal to probability of A plus probability of B minus probability of an empty event, and probability of an empty event is 0.
0.
So it's just probability of A plus probability of B. So this is something that we're going to use now. This is something that we're going to use. And the other thing that we're going to use is that for independent events, probability of A intersection B equals probability of A into probability of B. We studied this earlier, and let me mark this. So that's the first thing that we're going to use. And the second thing that we're going to use is that for mutually exclusive events, probability of union equals sum of the individual probabilities. Okay. Let me ask you a question. Are mutually exclusive events independent?
Yes, sir. मैंने यही पूछा था कि इंडिपेंडेंस में मुझे किसी से क्या फर्क है?
So you tell me, are mutually exclusive events independent?
सर ये कंडीशन सेटिस्फाई नहीं करते हो प्रोडक्ट वाली.
How?
A इंटरसेक्शन B 0 होगा। तो अगर A और B के प्रोडक्ट में कोई एक भी 0 नहीं होता तो हमें 0 प्लेन नहीं होगा।
Yes, that's true. But what if both are 0? Can both be 0? आप ठीक सोच रहे हैं. That's right. You can look at the formulas and say, but I want you to think intuitively. Mutually exclusive events, क्या ये independent होंगे या dependent होंगे?
सर इंडिपेंडेंट होंगे।
Mutually exclusive events. Let me write this in red.
नहीं भी हो सकते।
Let me write this in red and let me write this with a larger pen.
डिपेंडेंट होंगे इन द सेंस कि अगर हेड आ गया तो टेल नहीं आएगा, तो टेल के नहीं आना वो हेड के आने पे डिपेंड कर रहा है।
Absolutely, बिल्कुल सही कह रहे हैं आप. Mutually exclusive events are absolutely not independent. इनसे ज्यादा डिपेंडेंट हो ही नहीं सकते कोई भी इवेंट. दे आर डिपेंडेंट. Is a head influencing the tail? Is a head influencing the tail?
Yes, sir.
Because if I tell you that I got a head, it means you cannot get a tail. That's dependent. If I tell you I got a 3, it means I didn't get the other 5 numbers. That's dependence. So mutually exclusive events are absolutely dependent. They're not independent. This is a mistake that many people make for many years. मुझे डर है कि आप मुझे ये बताने के बावजूद you will still confuse these two concepts. But so just keep this in mind. If they're mutually exclusive, they're dependent. They're not independent at all. Okay. और जब भी ये सोचना हो, just think about head and tail. If you get a head, then you cannot get a tail. It means you've influenced the tail now. You cannot get it. The chances of tail are 0 now because I told you got a head. Okay. Okay, that's with that out of the way. Let's return to let me give you something called a Bernoulli experiment. Now don't get scared of the name. This is just the name of the scientist that studied such phenomena. Okay, it's just the name of the person. Bernoulli experiment. But what is a Bernoulli experiment? A Bernoulli experiment, the shortest description of a Bernoulli experiment is a coin toss. That's it. A coin toss is a Bernoulli experiment, right? A coin toss is a Bernoulli experiment. An experiment in which the output can be either 0 or 1. Either head, let's call tail a 0. So either tail or head, fail or pass. Like any experiment in which there can be only 2 outcomes. Any experiment in which there can be only 2 outcomes. That's a Bernoulli experiment. And in a coin toss, you have 2 outcomes. That's a Bernoulli experiment. Okay, is that clear? Bernoulli experiment?
Yes, sir.
Only only two outcomes. Great. Now something similar, a Bernoulli process. A Bernoulli process is a sequence of Bernoulli experiments. And if Bernoulli experiments scares you, replace this by a sequence of coin tosses, because each Bernoulli experiment is a coin toss. Okay, so it's a sequence of coin tosses, but importantly, using the same coin. It's very important. Same coin. Why do I say the same coin? Because in a Bernoulli process, you want the probability of heads on each experiment to be the same. For each toss. Okay, so any sequence of coin tosses using the same coin, so that the probability of heads is the same for each experiment. That's a Bernoulli process. Any questions here? Are there any confusions? कोई सवाल? ये तो सिर्फ मैं describe कर रहा हूँ कुछ experiments और एक process को. And the final thing that we have to study, that's called a binomial experiment. And I'm just giving it a name. You have already studied this binomial experiment in this course. I'm just giving it a name now. In a binomial experiment, it's a Bernoulli process. Of n coin tosses. You have a coin, you toss the same coin n times, and recording the number of heads. When you record the number of heads, now it becomes a binomial experiment. So let me give you the steps. In a binomial experiment, you toss a coin n times, and then you record or count the number of heads. That's it. That is a binomial experiment. यहाँ तक कोई सवाल?
सर बर्नौली प्रोसेस और बायनोमियल एक्सपेरिमेंट में क्या फर्क है?
Only this. When step number 2, you're recording the number of heads. That's the only difference. Well, there are two differences. A Bernoulli process can be infinitely long. In a Bernoulli process, you don't say how many times do I have to toss. But a binomial experiment ends after n tosses. You tell me how many times do I have to toss the coin, and then I toss it n times. That's one difference. But even this n times, it was a Bernoulli process that lasted for n coin tosses. It was still a Bernoulli process. Okay. But just remember, for binomial experiment, toss a coin n times and count the number of heads. That's the second difference.
ठीक.
Okay, can you tell me what can be the possible number of heads? Like, what is the sample space for a binomial experiment? What am I recording after my experiment? When my experiment ends, what do I have?
Number of heads.
Number of heads. So what can the number of heads be? What are the possible values of the number of heads? Quickly. All possible.
N.
No, give me the values. Give me the elements of S.
दो
Anyone?
ट्यूपल्स पे कंसिस्ट करेगा राइट और टेल.
No. Anyone?
सर 0 से n तक सारे वैल्यूज होंगे.
You could have 0 heads. You can get only 1 head. You can get 2 heads. How many heads at the most?
N.
You can have maximum n heads. So that's what a sample space for a binomial experiment looks like. Okay. Okay. Let's return to the question that I asked earlier. Okay. The one that we had to study. Recall that this was the question that I said we're going to study. 3 heads in 4 tosses of a biased coin. 3 heads is like an event. But what kind of an experiment did I conduct? 4 tosses of a biased coin. Is there a name for this experiment?
N tosses.
Is there a name for this experiment? Four tosses of a coin. And then
Binomial experiment.
this was a binomial experiment, right? So when I said 3 heads in 4 tosses of a biased coin, this implied that I had a binomial experiment with n equals 4 because I tossed it 4 times. Then equals 4. And we denote the probability of heads usually with probability of head on one toss. We just denote it by P. P can be half. P can be something other than half. If P is half, it's a fair coin. If P is not half, then it's a biased coin. Okay, so how do we find such a probability now? Now, how do I answer this question? What is the probability of 3 heads in 4 tosses? How do I proceed? From here onwards, we'll do it next time, and yeah, from here onwards we'll do it next time. For the next time, can you come up? So let's say we have a sample space S1. You have to fill this sample space before the next class, and let me tell you what this sample space is. I am tossing a coin 4 times. 4 times. And that's it. And I'm just recording what I got. I'm not counting the number of heads, okay? I'm not counting the number of heads. I'm just recording what did I get after 4 tosses, okay? I want you guys to write this whole sample space S1. What can you get after 4 coin tosses?